Hi everybody, I'm Professor Adam Teman of the EnICS Labs at Bar-Ilan University, and today I'm going to show you a demonstration of gate-level simulation, timing back annotation, and power estimation. Okay, so let me give a short introduction here. At this point in our demonstration, what we've done, we've written our RTL, we've performed at least very basic functional verification through some sort of a direct test or something like that, and we synthesized our design. So now we have a synthesized netlist. So we have a netlist that is mapped to standard cells. And now we're going to perform 3 steps for further verification and analysis. First, we're going to perform gate level simulation with a zero delay model. So we're going to run a gate level simulation on our netlist and make sure that it still works after running synthesis. Then we're going to go and back annotate our timing from our synthesized design. So we actually have real delays and so forth. We're going to stick them back into the simulation and see that, again, we don't have any type of timing violations and things still work. Finally, we're going to run static vector-based power calculation. And I know that I said static and it sounds like dynamic because it's vector-based, but bear with me, I will touch on that later. So let's start with what gate level simulation is. So gate level simulation, or GLS, is a direct test that's run on a structural netlist, a gate level netlist, so that might be called GLV. So this is a netlist that's constructed exclusively of standard cells, and we can run this at any stage from post-synthesis to post-place and route. We export our netlist from our tool, and then we can bring it back into the logic simulator and run our simulation on it. Why would we do such a thing? Well, it can ensure desired functionality is not lost in the translation from RTL to gate level. And we can ensure that timing delays do not break the intended functionality. These seem kind of strange, but I'll give some specific motivations for that. Okay, so first of all, if we make all kinds of mistakes or miswritten SDCs, then we can cause problems that will not show up in static timing analysis. For instance, we could actually put a false path on an important path, and it would not optimize timing and not check timing on it. And if we're lucky that we're running gate level simulation with timing back annotation, we'll see such a false path. There also might be unconstrained paths, which is something that we should be checking. But if we accidentally didn't constrain a path, then it will not be optimized for timing. Verifying system initialization and reset sequences, including power intent. So this is an important thing because when we turn on our system, that's really a high point of failure. So at least at the very minimum, we want to check that we can boot up our system and take it out of reset at gate level. And this is also important because when we do low power things that I'm not going to really be discussing here, but putting in all kinds of power gates and retention flops and all kinds of things like that, we need to see that the power intent that we had when we were designing our things actually came out and is still functional correctly when we have our final design. Okay, there are some simulations that only become relevant after we wrote our RTL. So we ran simulation and verification and so forth when we started, at the RTL level, and everything was behavioral. But now we've added all kinds of things after running the whole place and route. For example, design for test structures and just things with our clock tree, which may have been ideal before that. So different things come in after doing a whole place and route flow that are different than what we had in our RTL, and we want to see that we didn't break anything. There are things like asynchronous interfaces and multi-cycle paths, which aren't exactly checked by SDC. Maybe if we build the SDC in a certain way, we check it to some point, but this will actually be able to simulate these things with actual timing. And the last thing which we're going to show today is capturing switching activity for power estimation. So let's discuss some types of gate level simulation that we have. So the first one is the kind of trivial one, which is zero delay simulation. We run xrun minus no specify, which means don't deal with any of the timing that may be somewhere in some sort of design. Okay, and that simulates the netlist without annotating any timing data. So all of the gates are completely ideal, and we don't do any timing annotation. That's what we ran during RTL and so forth. So inside our behavioral models of our standard cells, there's going to be something called a specify block, which is really going to tell how we should actually put timing annotation on it. So writing minus no specify will say just ignore these specify blocks altogether. Okay, and we use this for system initialization and reset sequence, DFT verification, verification of power up, reset operation, and power domains, etc., because it's the easiest type of gate level simulation in term of runtime. Okay, the second type would be a unit delay simulation, and this is, okay, we're not going to put timing, but we'll add a small unit delay to each and every standard cell, and it's more simple than actually putting on timing, but it gives some degree of delay, so it can reveal all kinds of things like races and loops and so forth. It's not commonly used though. The one that is commonly used, if we can, the problem is it's computationally heavy, is called SDF back-annotation. And this annotates the gates and nets with delays from our static timing analysis and from our extraction. Okay, so this is used to verify clock tree synthesis, desired frequency verification, STA tool limitations, revealing glitches, power estimation, and all kinds of things. And the way we do it is we add this $SDF annotate command inside our actual RTL files. There are several ways to do it, but this is the main way that we're going to demonstrate today. Just adding $SDF annotate, and we'll see that in the scripts. So we are back now at the simulation, and we are going to simulate a gate level netlist. So we'll go over into scripts, and under scripts we have the Xrun options RTL, which we done before, and now we have the Xrun options GLV, which is going to do the gate level simulation. And in here we see that the Xrun options have several options. The first one that we see here is -define gate level. That's going to send a definition of gate level to the RTL, which we're going to see how what it does in a moment. Second of all, we have this def param smtb.width equals 4, which is going to send a parameter of width equals 4 to the test bench. Third of all, we're going to read DUT source list GLV versus the source list RTL that we read before. Finally, we have this -no specify. -no specify is going to tell the simulation that we're running a zero delay simulation. Do not read any of the specify sections of the Verilog files, basically of the standard cells. Okay, so I'm going to now go and open up our in our source code. We said we have our DUT source list over here with gate level, and in here we read in our standard cell library, which was very important to read in before. Okay, and then we also will go over and look at our test bench SMTB. And in SMTB, first of all, for the top module, we had a parameter that was width, and it was by default 5. But when we synthesized, we actually synthesized with a width of 4. And so this is going to be overwritten by what we showed before inside the script, that it's passing the parameter 4 into the module. However, when we go into our actual DUT, the DUT doesn't have parameterization anymore as it did in the RTL. So what we did before is we passed the parameter width to the DUT, but now we actually have synthesized gates. There's no parameterization. So when gate level is defined, what we have to do is instantiate the state machine without any parameterization. So that's what we saw over there. Okay, so again, going back into our Xrun options, gate level, what we see here is we defined gate level. That made it remove the width definition from the instantiation of DUT, and the def param here passed the width to the test bench itself. Okay, and we loaded the source list GLV, which is going to have all kinds of instantiations of the Verilog files for the behavioral models for different types of leaf cells that we used, such as standard cells or memories or so on. Okay, so now I'm going to go back and run the simulation. So all I do is xrun -scripts -f / scripts, and we're going to do xrun options dot gate level. And what it's going to do, it's going to run our simulation very quickly. It's a very short simulation, and it's going to now load SimVision again, run the simulation, and I've set it up nicely to open our waveform viewer and a design browser in a kind of a nice way over here. And first of all, what we see over here is now there are all these library cells that are read into the simulation. Second of all, when we look at the SMTB, under it we have our DUT, just as before with the same signals and everything. But underneath that now we have this library cells, which is going to have all the library cells that we just read. And it also has, as you can see, all these nets and so forth that were created by the simulation and are now inside our gate level netlist. So we are running on the netlist. We're not running on the RTL anymore. If we go up to the waveform viewer, we have the same thing we set up before, with the mnemonic of decimal over here on the count. And we see that it looks kind of okay. So we're going to zoom in over here, and we do see that we counted up to 16, and then it overflowed, and then at the second reset what we did is we counted up to 4 and then counted down and overflowed. So our gate level simulation worked, and that is what we expected, and that's very good. Another thing that we just see is that there is a 0 delay. So you see that there was a rising edge of the clock and there was no delay over here, even if we zoom in as much as we can. So this is a 0 delay simulation. So let's discuss SDF back annotation. Timing back annotation is done with what we call an SDF file, which stands for standard delay format. Okay, in Genus and Innovus, we're going to use the write SDF command to write out this standard delay format, and that's going to come from the extraction and timing analysis that we did. So in synthesis, basically, it's going to spit out all of the cell delays that we figured out during static timing analysis. After place and route, it will also have the wire delays that we got from parasitic extraction. Okay, so the SDF file has delay information for every instance, wires, timing checks, and so forth. So it looks something like this. So an instance would start with a cell command over here. It would say what type of cell it is, what the instance name is, and then it will give us a list of all the types of delays through it. So I just gave one example here. It'll say there's an IO path from clock to Q, and these are the best case, typical case, and worst case timing of these in 3 different corners. Okay, there also could be timing check commands, which will say what our setup and hold requirements are, and then our simulator can actually spit out setup and hold violations if there are those types of things. Next, we have wires, and wires are also started with a cell command, but they give the cell type a hierarchical type of a module, and then they just give a delay without an absolute delay for an interconnect delay. So these are, this is a wire that goes from a port to a pin on a cell. That's the wire, and it says what the delays are. Okay, and here's from a Q of one register to a D of another register, says what the delays are, etc. So that's the type of data we're going to find inside an SDF file. Of course, it's a very complicated type of syntax, but those are the main things that you see inside. We don't tend to sit there and read this. It's spit out of our tool, and then we read it in to the simulator to actually apply these delays onto our simulation. So in our Verilog test bench, as I said before, we add this $sign SDF annotate, and that reads the SDF file. So what does it look like? We put an initial block inside our test bench. We write begin $SDF annotate. We give the name of the SDF file, the path to it. Okay. We give the module name that the SDF was extracted for. These 2 commas there are on purpose. Then we have this sdf.log. That's where it's going to log. That's the file that's going to write out the log of the SDF back annotation. And maximum is going to say that we want to annotate the maximum values out of those 3 we had: minimum, typical, and maximum. Remember, there were 3 numbers, or up to 3 numbers inside the SDF file. Okay, then we run our simulation with the SDF flag. So at xrun, we add this plus SDF verbose and minus SDF stats and give a file name, and that's going to write out a lot of data, report a lot of things about the SDF, and what the statistics are is going to write it in a different file. Finally, when we open up our waveforms, we can see actual delays. So here was a rising edge of a clock. There was a long delay, and the data only started to change here, and it actually glitched around or wiggled around for a while until it finally stabilized at some point, hopefully before the next clock edge. So that's the type of thing that we will see, whereas before, immediately at the rising edge of the clock, we would have had the change after our combinatorial cloud. Our next step is going to be running a timing back annotation. So we have another file here called xrun options back annotation, and in it we see we don't have that minus specify anymore, because now we do want to back annotate the timing to the specify parts of the Verilog modules of the leaf cells, of the standard cells, and so forth. So that is what is going to enable us to actually add timing to our behavioral models of our standard cells. We still have this defined gate level, but we added an additional defined back annotation, okay, which I'm going to show you in a second. Second of all, we provided another define that's called SDF file, and it's going to write into export post-syn. It's going to write it's going to read sm_postsyn.sdf, which came out of Genus. Okay, so if we go back to our Genus script, going down to the bottom, we had here write SDF to design post-syn SDF. And that was basically the file that we can find over here, sm postsyn.sdf. So let's look at this file for a moment. And what we can see here is that we have the header over here that's saying what the file name is and the version and when it was created and what created it, what the voltage, process temperature, time scale, and so forth were. And then it's going to start by listing the cells. So there's a cell over here that's a NOR cell, and it has its ports and the which have some sort of delay related to them, and it has the IO paths, like the A to Y path, B to Y path, and C to Y path, each have some sort of delay related to them. And as you can see here, by the way, there's a place for 3 numbers over here. That's what the colon is. It's separating between 3 numbers in a list, and that would be a best case, typical case, and worst case. We only wrote out the SDF for the worst case, for the slow corner, so that's what we have here. And in this file, what we have is only the cells, which have their instance names that were given by Genus. The G comes from Genus. There are no interconnect delays because we do not have interconnect so far during synthesis. But if we had exported the SDF post place and route, then we would get the interconnect delays as well. So that is the SDF file. Going back to our xrun options back annotation, so we read in the same F file. We add this plus SDF verbose, and that's just supposed to write out all kinds of things to our log file about the SDF, about running SDF. And minus SDF stats is going to create a report file called SDF statistics that we can also look at. Okay, and finally, we provided a different script. This one is called back-annotation.tickle, which is going to do things a bit differently that we'll discuss a bit later. Okay, so I'm going to go now back to my, my test bench. And in my test bench, I had an if-def of back annotation. And now we define back annotation. And so what I'm going to do is going to use this $SDF annotate command in order to run this SDF back annotation. And what we receive here is the SDF file that, as you saw, we passed from our script into here as the place that we wrote out our SDF, this export postsyn SDF, sm.postsyn SDF, right? DUT is the scope of the SDF. That's basically the name of the module that we want to back annotate to. You can have different SDF files for different modules, and therefore you can use this SDF annotate to take the SDF from different files and write them into the simulation. This is the name of the log file, and we're going to take the worst case, so that is called maximum. There are purposely 2 commas here because we're missing another parameter that we don't care about over here. So the 2 commas are just because there is it's an empty parameter over here. So now when we run the test bench, we're going to both instantiate the DUT as we did a moment ago, but we're also going to read the SDF file for back annotation. So now we're going to go back to our console and run the SDF back annotation. So it's going to be srun -f ... script xrun options, and we're going to choose the back annotation one this time. And it's going to do a similar compilation, elaboration, and so forth, and run. And so far it looks like it's running okay. Let's see if it runs the whole thing. So it's opening SimVision now. Now it's running the simulation, and Well, it kind of looks good. So let's go back over here and see how good it looks or not. So again, if we look at the design browser, we have the same thing we had before with the library cells and the names that come from the gate level netlist. So that's the same as before. But now we can go over to the waveform viewer. And in the waveform viewer now, I didn't use the same command setup that I did before. So let's change the mnemonic over here again to decimal. But what I can see here, that it looks good just from a first kind of view of it. But now I can zoom in over here. So I'm going to zoom in, and I see that what happens here is that we have a rising edge of a clock over here. It takes a while for things to change, and that is the delay that we see here. So if I go out and I zoom into different areas, I can see that there is a rising edge of the clock over here, right? But we see that there is actually kind of so this is the rising edge of the clock. There is a glitch over here, right? There's a race between two signals before it actually stabilizes. So it turns from whatever the value was over here. The value was 11. It turns for momentarily to 8, and then it stabilizes at 12. This is the SDF back-annotation. This is the timing that we see going over here. But in general, if I do zoom into the whole thing, I do see that it gets 1, 2, 3, 4, 5, etc. until 16. Though if I look closely, I do see those types of glitches and the delays of signals. So the back annotation does look like it's working properly, and our design is still working properly under timing. As we can see, we had the behavior that we expected. Okay, so again, looking into here, we do see that in certain places it does take a while to stabilize. There are, you could call these glitches. Now, depending on our inertial or transport delay options, these types of glitches may not even go through the standard cells, depending on their widths. Going back to our console, I just want to show you that what we have here now is we have an sdf.log file. Okay, so we can look into that sdf.log file, and we see that there is the SDF annotation of this thing, and it's showing us how it is annotated in here. Okay, we also saw that we were going to write to the reports directory about the SDF statistics. So you see that there's this SDF statistics file. So we'll go into the reports, SDF statistics, and again, it shows all kinds of things. There is a list of unannotated paths and so forth, but there aren't a lot of them. Most of the stuff was annotated very well, and we'll see that in a moment when we do the power estimation. One more point over here is glitch propagation or delay models. So zero delay simulation propagates the signals through the logic gates immediately. But once we add the delays, varying arrival time create glitches. And we saw that actually in the previous slide where we had these little changes until the signal stabilized. And the thing is that what digital gates do is they actually filter out such glitches. So if we have a really small glitch, like a really small pulse where for a very short amount of time, you know, an AND gate changes from 0 to 1 and then goes back to 0 or something like that, then the next digital gate may not pass that through. So how is that taken care of in simulation? And that's what these delay models are. There are two types of delay models that simulators usually support. One is called transport delay, and in this case we completely ignore the fact that digital gates are filters. Basically, signals automatically propagate through gates after a delay. There's no filtering done. So the output waveform is going to completely copy the input waveform. On the other hand, there is this thing called inertial delay, which is typically used, and then the signal is filtered if the input signal has a short pulse. But how short a pulse? Well, we set a threshold for this, and the threshold is relative to the delay of the gate. So if the gate has a delay, let's say, of 100 picoseconds, then we can say that pulses that are shorter than 100 picoseconds or shorter than 50 picoseconds or something like that will be filtered out. And the way it's done in Xcelium is with minus pulse R and minus pulse int R and minus pulse E minus pulse int E, where the R is for reject. So a glitch pulse that is shorter than some percentage of the TPD of the gate will be rejected and will be filtered away, while int is for interconnect. So that's the interconnect will not pass it. And pulse E will actually cause an error. So if we get a pulse that's shorter than a certain amount, then we can flag an error, and that's for if we think that this type of a glitch could actually harm our simulation. So usually we would use something like minus pulse r to cause this filtering, and that can really affect different things like the power estimation, because glitches can be very dominant for power.